Hello everyone, I'm Koshal. I'm glad to share our research with you today, diving into Windows HTTP, unveiling hidden Preauth vulnerabilities in Windows HTTP services. We work for Cyber Kunlun and Huazhong University of Science and Technology. We have been focusing on cybersecurity research for years. Here's today's agenda. First, we will introduce the background of our research and give an overview of the HTTP service framework. Then, we will share the details of several logic-based DOS vulnerabilities and the tricks we used to find them. After that, we will talk about the details of remote code execution vulnerabilities of HTTP services. Finally, we will end with a brief summary. First, let me introduce the background of our research. We focus on researching Windows HTTP services mainly because almost all of them can be accessed without pre-authentication. They don't require user interaction and extra configuration. Most importantly, many default services are built on top of HTTP APIs. This means if there are any vulnerabilities, they could lead to serious problems. Let me briefly introduce HTTP services. Services based on HTTP APIs use functions like HTTP create server sessions function and the HTTP add URL function to register various HTTP service information. After these HTTP services are registered, we can use HTTP query service configuration function to get various information about them. We can easily use the netsh command to get information about all HTTP services. This helps us quickly identify targets for vulnerability research. In the second part, I will share the framework of HTTP services. Web applications based on HTTP APIs interact with the kernel component HTTPCs through interfaces provided by HTTP APIs. These interfaces use device I/O control function codes with specific I/O control codes. Finally, HTTPCs handles tasks like receiving and sending HTTP protocol data. Here's a simple framework of HTTP services. All Windows HTTP services based on HTTP APIs work under this scope. This is the simplest and the most common HTTP service processing flow. It's worth mentioning that almost all HTTP API services don't require pre-authentication. Only a very small number of services authenticate clients after receiving the HTTP headers. Using NTLM or other authentication data in HTTP headers, but even in those cases, the receiving stage itself doesn't require authentication. HTTP services involve two important HTTP API functions. The first one is HTTP receive HTTP request function, which is responsible for receiving HTTP header data. The service calls HTTP receive request entity body function to receive the HTTP body, such as in receiving post data situations. To summarize, here's the general HTTP service processing flow. Now that we understand the HTTP service framework, I will share some logic-based DOS vulnerabilities caused by incorrect use of HTTP APIs. For DOS type vulnerabilities, crashes caused by memory corruption are not the only concern. For an HTTP service, if the server stops handling normal client requests, that's also a form of DOS and a high impact. First, I focus on the receiving stage of HTTP services. Different services use different receiving methods, which I grouped into three types: one sync receiving method and two async receiving methods. Here's an example of sync receiving. Its main feature is using a single thread. I will introduce CVE 2024-43512. In the vulnerable function, HTTP receive HTTP request is set to receive a fixed length of 0x1360 bytes for the HTTP header. When an attacker sends an HTTP header longer than 0x1360 bytes, the function returns 0xEA, which means the receive buffer is too small. Normally, the service should update the buffer and length. They call the receive function again. But this service doesn't update the receive buffer size. It stays at 0x1360. As a result, the service keeps looping, trying to receive data but never accepts data from other clients. After the vulnerability is triggered, normal clients only receive timeout errors. The second type is async receiving. In this method, receiving is still done by a thread within the service, but it doesn't wait inside HTTP receive HTTP request function. Next, I will introduce CVE 2025-27471. The UPnP service is a typical example of this kind of async HTTP service. Since HTTP receive HTTP request function is handled through async method, this causes a time gap issue. When an attacker sends multiple malicious requests at the same time, HTTP receive HTTP request function doesn't return 0 or 0x3E5 as usual, but instead returns an error early. This means number of bytes transferred is not updated after it's initialized as 0. If the error returned is 0xEA, the receive length is set to 0 instead of the correct value, which is set with getOverlapped result function. We can observe this logic issue by setting a conditional breakpoint to print the return value of HTTP receive HTTP request function. When the problem is triggered, the function keeps returning an error forever. Even if the attacker disconnects, the function will continue looping endlessly. As you can see, normal UPnP client requests receive proper HTTP responses, but once the vulnerability is triggered, clients can no longer communicate with the server. The third async method, which uses registered callbacks. This is the most common way to handle HTTP requests in Windows services. With this method, multiple threads can handle requests from multiple clients at the same time. This is a common callback handling pattern. I have listed some common callbacks here. It's important to note that some callbacks are optional. These callbacks are registered based on the service's needs. In the first two receiving methods, which use a single processing thread, if the receive function stops being called to get new requests, it leads to a DOS issue. For the multi-threaded callback method, after a function finishes processing, it creates a new thread in the thread pool and calls the receive function again. But here, I want to mention another DOS technique to consider. Since the number of threads in the thread pool is fixed, if each thread, after finishing processing, doesn't call start thread pool IO function to create a new receive thread in the pool, but instead just returns, that thread will end. When there are no receive threads left in the thread pool, the HTTP service will stop handling normal client requests. Next, I will introduce a vulnerability in the function resource service. In this service, I/O result is the return value of HTTP receive HTTP request function. When it is 0, it means the HTTP request was received successfully. The service processes the request normally and finally calls issue receive request function. Inside this function, start thread pool IO function is called to create a new thread in the thread pool, which then calls the receive function to wait for new requests. However, when IO result is not 0, meaning there was an error receiving data, the function returns immediately without creating a new thread. This means that by repeatedly sending corrupted packets causing IO result errors, all threads in the thread pool will exit. As you can see, before the vulnerability is triggered, no more requests receive HTTP response packets. But once the vulnerability is triggered and all threads in the received thread pool exit, all no more requests will time out. I reported this vulnerability last year. MSLC considered that although it's pre-authenticated BOS, the service is thought to be enabled only within trusted networks. Therefore, they rated it as a low severity. In the receiving stage, I introduced 3 cases. Using these tricks, I found many similar issues in Windows HTTP services. From studying these vulnerabilities, I believe that for HTTP services, the handling functions should never stop receiving. In other words, after any request, whether valid or invalid, the service must call HTTP receive HTTP request function with request ID set to 0 to wait for new client requests. It's especially important to carefully check the function's return values and to properly update and validate the receive function's parameters. Next, we focus on the response stage. Here, 2 functions are involved. The first one is HTTP send HTTP response function, which sends the HTTP response packet. HTTP console HTTP request function forcibly disconnects the client, causing the client to receive an error. The connection between client and server is actually established in kernel driver. It creates a non-page pool through allocate connection for look-aside function and initialize some required structures. Similarly, when the server actively disconnects, it calls free connection for look-aside function to close the connection, release related structures, and decrease the reference count of connections. When I reached this point in my analysis, I wondered what happens if the server doesn't actively close the connection. In other words, what if it never calls HTTP send HTTP response function or HTTP console HTTP request function to close the connection? I found this situation in some services. After receiving and parsing data, they don't call HTTP send HTTP response function or HTTP console HTTP request function, and instead immediately starts receiving new data. When I debugged the kernel, I saw that HTTP doesn't close the connection or decrease the connection's reference count. This can lead to non-paged pool exhaustion in kernel. Here I take the BranchCache service as an example. The related function has documentation available on MSDN, which defines the structures for different types of poster data. In the poster data structure, we can specify what kind of data the service should handle. When we send corrected data, the service throws an exception using the throw helper function. Then, the service calls HTTP receive HTTP request function in the registered callback to receive new data. but it doesn't call HTTP send HTTP response function or HTTP cancel HTTP request function to close the connection. This causes the connections in HTTP to remain unreleased. Here is a simple demo. First, using NetSH, we can see that the BranchCache service is running along with its URL and the server's IP address. Next, we run the POC from unauthenticated client. You can observe the non-page pool growing, which eventually leads to a full system DOS. These types of vulnerabilities cause the non-page pool to be exhausted, leading to system harm or BSOD. I believe the service must always respond after processing, whether success or fail, by calling a response function, or actively close the connection using a registered disconnection callback. Finally, let's talk about IIS. IIS is a framework, and it itself is also a service built on top of HTTP APIs. IIS provides a basic framework for some web services, helping them handle receiving and responding to requests. Web services only need to process data through IIS API extensions. It's worth mentioning that common web servers using C# or .ASPX are also supported at the core by Windows built-in IIS API extensions. Through IIS API and CGI restrictions, we can find the IIS API extensions used by different services. For services running on IIS, when a client sends an HTTP request, IIS uses a command to start W3WP process for the corresponding service. Once the service is running, we can also see its process via NetSH. In this process, a very important data structure is IIS API context. For each service on IIS, when W3WP process is created, an IIS API context structure is also created. When the IIS service exits, the IIS API context structure is released. For this structure, each time a request arrives for the specified service, IIS checks the reference count of the structure. IIS sets a reference limit of 0x1366. If the reference count exceeds 0x1366, IIS returns a 503 service unavailable error. During receiving, IIS can handle the data reception, but the IIS API extension DEL must decide when to send the HTTP response to support this. IIS provides the server support function, which is a dispatch function with different branches for various needs. To ensure the IIS API context reference count remains balanced, some branches in server support function will decrease the reference count of IIS API context. Because server support function manages the IIS API context reference count, and this function is used by different services on IIS API extensions, the IIS extensions must be very careful when using it. Incorrect use of server support function can cause problems with the reference count, such as premature release leading to use after free or denial of service. Next, I will share CVE 2024-38067. OCSP is a service running under the IIS framework. OCSP IIS API is its IIS API extension. It processes post data from client and the responses result back to client. So finally, OCSP calls server support function within send response to client function to send the HTTP response. In the branch of server support function, the server first calls the flash function. Finally, in post-completion function, the reference count of IS-API contacts is decreased. However, if an attacker's client disconnects early, after sending the posted data but before receiving the server's response, the flash function returns an error. As a result, post-completion function is not called, and the IS-API contact's reference count is not decreased. When the reference count reaches 0x1366, the OCSP service will stop processing any requests. Before the DOS is triggered, normal requests receive responses. After it's triggered, clients will get a 503 service unavailable error. These types of vulnerabilities also cause the permanent DOS. More seriously, user-free bugs caused by reference count issues are common. If IS-API extensions use server support function carelessly, similar problems can lead to remote code execution. When developing IS-API extensions, we must pay close attention to the reference counting of structures when using IS support interfaces. I have introduced the logic-based DOS issues in the receiving and response stages of HTTP services. Next, Victory will present the RCE issue in HTTP services.
Thanks for Koshio's wonderful speech. Now, I will take over to continue the presentation discussing fascinating RCE cases. First, I will introduce the HTTP service of KTC Proxy Service, abbreviated as KPS. It provides a mechanism for client to use the proxy server to change passwords and securely obtain Kerberos server tickets from a Kerberos server. The client establishes the connection with the KPS server via HTTPS. Then the server resolves the IP address of the domain provided by the client. Subsequently, KPS establishes the socket connection with the KTS server indicated by the IP, acts as a channel forwarding messages between the client and the KTC server. Here are three columns of content. The first column lists the HTTP APIs used in the server. The second column shows the callback functions the server invokes after events registered by the HTTP APIs occur. The third column displays the events that trigger these callbacks. As you can see, this is an asynchronous callback-based HTTP architecture. When the server calls, HTTP receive HTTP request. If a client initiates a connection request, the server process triggers the KPS HTTP receive request IO completion callback function to handle the new connection request. If the server is configured with the client certificate, it waits for the client to send the request with the certificate. Then the server calls HTTP receive request entity body to await the client's message. If the client sends a message, it activates KPS receive request entity IO completion function, which continues processing the client's message. Since the service does not register HTTP wait for disconnect, the server does not respond when the client disconnects the HTTP connection, leading to new issues, though this is not our main focus. When the server itself calls cancel HTTP request, it subsequently triggers KPS HTTP cancel request IO completion callback function in a new thread. A server can use HTTP send response to send the messages to the client, and upon send completion, two callback functions are triggered. Once the connection is established, the server calls ds_get_dc_name function, which queries the DNS server to obtain the IP corresponding to the domain. Suppose the client provides the domain testyours.zz. It will query two SRV records. Assume the server returns abc.testyours.zz. Then it accesses this address using LDAP protocol to query the Kerberos server address, say abcd.testyours.zz. After obtaining this address, in a subsequent process, the server calls the MSAFD interfaces socket to connect to our spoofed Kerberos server. At this point, the KPS server acts as a client. When it receives messages from the fake Kerberos server, three callback functions are triggered to process the received message. Next, let's discuss the case CVE 2024-43639. In the KPS socket receive data IO completion callback process, it encodes messages through several functions. Since the socket does not limit the length of received messages, the message length can be a 4-byte length. When calling the ASN1 incheck function, as shown in the diagram on the right, A2 is the current message length. On line 10, if A2 is greater than the word 18, its value is assigned to V9. In the next line, the word 18 and V9 are added, and the sum is assigned to V10, which is then used as a size to allocate memory. If the message length is, for example, FFFFFFB, and the word 18 is 5, then V10 will overflow to 0, resulting in a very small memory allocation. This leads to an overflow when writing to this small memory in the subsequent process. With proper condition and layout, this can cause RCE problem. Here is the crash stack trace. We can see that RCX points to a non-writable address. After discussing the KTC proxy server, let's move to another case, the Remote Desktop Protocol service and its gateway service. The Remote Desktop service is a built-in component in Windows, enabling users to remotely control Windows systems over network. This functionality is achieved through the RDP protocol using port 3389. However, Windows Remote Desktop Service also uses port 3387, which implements an HTTP service supporting WebSocket. It allows clients to complete a remote desktop protocol request via HTTP. Now, let's explore the remote desktop gateway service. As shown in the diagram, the client connects with the remote desktop gateway service via HTTPS on port 443 or DTLS on port 3391. After a series of negotiations and authentications, the gateway service forwards the client's remote desktop protocol messages to a corresponding remote desktop server. Now, let's examine the HTTP architecture of the remote desktop gateway service. The remote desktop server and its gateway both employ a similar asynchronous callback-based HTTP architectures. As you can see, it's similar to the KPS architecture, with the differences being that it has a registered callback function for handling connection disconnection, and callback functions for processing both WebSocket and non-WebSocket requests. Now, let's work through a normal connection process using this flow chart. First, the client initiates a WebSocket request to the server with a connection ID conID1. This triggers the server's HTTP receive request completion callback function. During processing, it calls process out channel or WebSocket request function, which allocates the new connection structure for this connection and stores it in a hash table. Later, it calls send HTTP response to send the messages to a client. Upon completion, the server's callback function, HTTP send response completion function, is triggered, which allocates HTTP server connection structure and binds it to connection 1. In the subsequent processing, it calls receive data, where argument 3 is a pointer with an offset from the server connection structure. Inside the receive data function, it retrieves the connection 1 from the hash table by using connection ID conID1 and assigns argument 3 to the buff field of a member in the structure. In later calls, through WebSocket receive raw data, it calls HTTP receive request edit body to register a new callback. When the server receives a message from the client, it triggers this callback. During processing, it calls WebSocket receive loop, performing a critical step, copying the received message to the address pointed by the buff field of connection 1's member, which is the offset of HTTP server connection structure. Then additional operations follow. So what issue might this architecture have? Can a client 2 connect to a server using the same connection ID? In fact, this is not okay, as process out channel or WebSocket request checks if the ID already exists in the hash table. But could we release the connection before the GET operation, then have client 2 connect using connection ID 1? It seems possible. Let's deduce what would happen. First, client 1 connects to the server with connection ID 1, and the server creates connection 1 structure. After sending, it creates HTTP server connection 1. Then it enters receive data. At this time point, we disconnect client 1. Since the disconnect callback is registered, the server automatically triggers handle disconnected, which dereferences HTTP server connection structure and removes connection 1 from hash table. HTTP server connection may not be released at this point, as a reference to it exists until handle sender response computation finishes. Then we connect with client 2 using the same connection ID, and the server creates connection 2 and storing it into the hash table. Now, return to the receive data thread. It continues running, retrieves connection 2 from hash table using a connection ID 1, and assigns argument 3 to the buff field of connection 2 structure. Then it calls HTTP receive request edit body to register a callback function. Then the handle send response completion function finishes dereferences CA HTTP server connection 1. So there's no references. And argument 3 will be a dangling pointer. Later, when client 2 sends a message to a server, it activates handle WebSocket receive raw data completion callback function. Inside the function, it retrieves connection 2 from the hash table using conID 1 and writes data to the dangling pointer. Thus, we can overflow to a dangling memory. Here is the stack trace at the crash site. As shown, it crashes in the memory copy function, with RCX pointing to a non-existent address. Finally, let me briefly summarize. Looking ahead, MSRC updated their SDL servicing bar for DOS-related vulnerabilities, so no bounty for resource exhaustion bugs. Second, logic-based DOS vulnerability is still in scope for high-value assets, including these targets. Third, RCE vulnerabilities are also common in HTTP services, especially during the passing of the post data, so try to fuzz it. Takeaways. First, apply useful technique across the entire attack surface to uncover similar issues. Second, DOS don't require crashes. Logic flaws in request handling alone can also permanently block services. Third, further reflection, the potential for DOS and even RCE may lie in a deeper, more fundamental logic of the target. Thank you for your listening. That's all.